Here's the Unit 7 progress check for rotational. The first question was one of the longer ones. The second one was the shorter, I think, paragraph one. We'll look at it in a second. So starting with the first one. It's a basic question about equilibrium. It shows the pivot, it shows 3 tensions, and it's at rest. So therefore, that means the sum of the torques must equal 0. And remember, torque is Fr sine theta. In this case, sine theta is 1 for all of these since theta is 90 degrees. So that means that F1 R1 plus F2 R2 plus F3 R3 must all equal 0. Also, the farther away the string is, the less force you're going to need. So using that logic, and again, that's because of this idea that torque equals Fr, all of these torques are 0 because it's at rest. So that means the larger the radius, the smaller the force. So to correctly rank these, I think it wanted 1 for the least tension and 3 for the greatest tension. C would be 1, B would be 2, and A would be 3. It's going to take more force at the shorter radius to keep that at rest. This was worth 2 points. 1 point for correctly using the logic that torque equals 0, or sorry, the sum of the torques equals 0 since it's at rest. And 1 point for saying that the larger radius means you will have a smaller force. So those were the 2 points for part A of that question. Now for part B, they hang the sign with a cable, but the cable breaks and the sign rotates clockwise. Here's our diagram showing what happens. So it wants to know at which time, if any, the angular acceleration is greatest and whether it is the same at all 3 times. So to answer this, we want to look at the relationship between torque and angular acceleration, where, wrong one. Here we go. Tau equals I alpha. So they have a direct relationship. Therefore, as torque decreases, angular acceleration will also decrease. In all 3 of these situations, so T1, T2, T3, you've got the force of gravity, or the weight, causing the torque. Also remember that torque is Fr sine theta. In this case, because the angle is changing, your torque will be changing as this rotates down. So therefore, the angular acceleration is not the same at all 3 times. And what we want to do is figure out when you're going to have the greatest amount of torque. Well, as theta gets closer to 90, sine gets closer to 1. Therefore, as theta is decreasing, your torque must also be decreasing. That means that your greatest amount of angular acceleration will be at T1. Physical explanation for that ranking. This was worth 2 points. 1 point for indicating the relationship between angular acceleration and torque, so they are directly related, and 1 point for explaining that the torque will decrease as this rotates down, because the only force acting on it causing that torque would be the weight, and the angle here will decrease as it gets closer and closer to being completely vertical. Okay, part 2. Show that alpha can be modeled with 3g sine theta over 2L. It gives us the rotational inertia of the sign. So just rewriting this. Angular acceleration equals 3g sine theta over 2L. I think that's S. And it also tells us that the rotational inertia equals 1/3 ms ls squared. We know that torque equals I alpha. We also know that the gravitational torque would be ms ls over 2 sine theta. I forgot the g. Let's fix that because this would be for weight. So this would be msg. So again, that's my torque. And that's going to equal my moment of inertia, 1/3 ms ls squared times angular acceleration. So ms cancels, and that goes away. So we are left with 3g sine theta over 2ls equaling alpha. So this question was worth 3 points. First thing they wanted you to do was to somehow show torque equals I alpha, so Newton's second law for rotation. Second thing they were looking for was a correct substitution for torque. So once again, where did it again? T equals FR sine theta, where the force is your weight, MSG. Your radius is always half the length of the rod, so that would be LS over 2, and then sine theta. So that's where this MSG LS over 2 sine theta came from. And then the third point would be for the correct substitution for rotational inertia. So plugging in this for our I, and then from there, just showing how we go from here and here to here. So that was worth 3 points. Next part, C. The students want to describe the angular velocity of the sine as it rotates, and they propose the following equation. Regardless of whether or not this equation is correct, does it make physical sense? So looking at the equation, and let's move all this. Omega t equals 3g sine theta over 2ls t. This equation shows a direct relationship between omega and time. In other words, as time goes on, omega will continue to increase. And that's not the case. So the angular velocity will not keep getting faster, because if you think about the rod, which is on a pivot, there's nothing stopping it from continuing to circle around clockwise. So the rod's going to keep doing that, and the angular velocity will change because you don't have a constant angular acceleration. We saw that with the previous problem, or 2 problems ago, where it was asking us to talk about where alpha would be greatest. So no, this does not make physical sense, because eventually omega will have to start decreasing, and that's 1 point. So 1 point for saying no. Omega will eventually get smaller. And then the second point is for saying that this equation only shows omega increasing. So no, omega will eventually get smaller. And this equation only shows an increase in omega. And again, that's because of the direct dependence between angular velocity and time. But remember, it will change and eventually get slower. So that's why this equation does not make physical sense. Okay, now for the last part of the problem, which is split between 2 slides, so I'll try and stay on the graph for as long as I can. It gives us an angular velocity versus theta graph in radians per second and degrees. And it wants to know which of the 4 proposed equations is correct. 2 of them have sine, 2 of them have cosine, And then if you look under the radical, the G and the L are varied, either numerator or denominator. So with those four combinations, we want to figure out which one is most accurate. So first we can look at the sine and cosine and figure out what's going on with this. So you have, just looking at this graph, an angular velocity that starts at 0 degrees, so angle of 0. You have a high angular velocity, and then it is decreasing as the angle gets to be 90 degrees. So what we're looking for with this angle is, as you have an increasing angle, your angular velocity needs to be getting smaller. Cosine of 90 is 0, sine of 90 is 1. So this would actually be cosine, because what you're showing with the cosine relationship is that as the angle increases, your angular velocity would be decreasing. So that leaves us with choice 1 or 2. And the next thing to look at would be whether the G should be in the numerator or the denominator. So I'm just going to go to the next slide to give us a little bit more room. And we know that omega should be in units of radians per second. So just looking physically at what these units show us, we'll start with the first one, which had, so it was the square root of 3g cosine theta over L. There. So units of G would be meters per second squared over L, which is units of meters. This would equal 1 over second squared, just looking at the G over L part. Cosine theta would give it to us in radians, so really what we would be left with here with that first one would be radians per second once you took the square root of that. Your next one, if you have the square root of 3ls cosine theta over G, we would be left with, sorry, this should have all been under a radical. We would be left with meters over meters per second squared, or the square root of seconds squared, which would leave us with seconds times radians. Running out of room. Let's erase that. When you take the square root. So the one that reduces to radians per second would actually be the first equation, which is on the previous page. Omega equals 3g cosine theta over L, square root of all of that. This was worth 3 points. 1 point for the correct equation and some attempt at a justification, even if your justification was wrong. So if you guessed and you still got it, if you guessed and you got it correct, but your justification was wrong, you could still get that point. 1 point for talking about the units, how the first equation, the units will work out for radians per second. And the third point is for showing that it is a cosine graph because of that increase in angle showing a decrease in angular velocity. All right, let's look at the next question now. We have, move this out of the way. Okay, so short for response question, we have a ramp where you have a hoop placed at the top, mass m0, radius r0 at the top. So here's our picture. To the next page, it wants us to show the force diagram for the forces exerted on the hoop as it rolls down the ramp. So there are 3 forces here. Your first force exerted from the center would be the weight or the force of gravity. So 1 point for showing that. Your second force going from the ground perpendicular. Let's try that again. Having trouble drawing straight lines. So perpendicular would be your normal force, And then the third force going up the incline, parallel to the incline, would be the frictional force. So 3 forces, 1 point for showing the weight coming straight from the center, and 1 point for showing the frictional force going up the incline, and also having the normal force perpendicular. So this was worth 1 point, and this was worth the second point. Next question says, after it's released, it rolls down the ramp, launches horizontally off the edge, and lands a horizontal distance d from the edge of the table. It's repeated, but instead of a hoop, you have a solid disc where the rotational inertia of the disc is greater than the hoops, but the mass m0 and radius r0 are the same as shown in figure 2. So here we go. And what this wants is a paragraph length response that explains which one, if either, will travel the greater horizontal distance once it's released from rest, rolls down the ramp, and launched horizontally off the table. Discuss the physical aspects of the hoop and disc that are similar and different, and how those differences affect the horizontal distance traveled. So this will look for 4 main things. 5-point paragraph. 1 point is, as usual, for a clear, coherent, relevant, consistent argument that follows the paragraph guidelines for the College Board. So really just write a paragraph that somewhat addresses the question. You should be able to at least get that 1 point. I'm going to go through what each of the 4 points that they're looking for are, and then I'll explain what a good response would be. So the first thing you want to say is that both the hoop and the disc have the same initial GPE. So they both start with the same amount of gravitational potential energy when they're at the top of the ramp. The second thing you want to say, because it is asking for how they are similar and different, is that they're going to be in the air for the same time. And that's because they are being released from the same height. Once they leave the table, they are projectiles. The only thing determining time is the height. So they're starting with the same initial gravitational potential energy. They're also going to be in the air for the same amount of time. Now, what's different? Because the moment of inertia of the disk is greater than the moment of inertia of the hoop, and it does tell us that, the disk is going to have more rotational KE. So more rotational kinetic energy for the disk, meaning less translational kinetic energy for the disk. So because of the disk's higher moment of inertia, it's going to have more rotational kinetic energy. That's because that's 1/2 I omega squared. Therefore, it's going to have less translational kinetic energy, the 1/2 mv squared. So that means it's going to have less speed. Because it has less speed, and we know that delta x, or distance, however far it's going to go, is going to equal that speed times the time in the air, the horizontal distance that it travels is directly related to that speed. Therefore, the disk will not go as far as the hoop. So the hoop goes farther due to the fact that it has the smaller moment of inertia, less rotational kinetic energy, more translational kinetic energy, therefore more speed when it leaves the table. Being in the air for the same amount of time means that the hoop will travel farther. So that's what they're looking for. Those are the 4 main points. So 1 point for saying they have the same initial gravitational potential energy, 1 point for some kind of statement about the kinetic energy at the bottom of the ramp, in other words, which one has more and why. 1 point for saying they're both going to be in the air for the same time because the height is the only thing determining that. And the 4th point is for saying that the hoop will travel farther because it has more translational speed, and distance is directly related to speed. And once again, that 5th point is for writing a clear, consistent paragraph. If in doubt and you have a paragraph response question on the actual test, just write a paragraph. Try and do as logical of an argument as you can. If you have no idea what you're doing, just say something about one of the concepts that the problem is asking.